From the first telescope to journeys beyond the moon, humanity has always looked up with wonder. Today, we'll explore 100 fascinating facts about space exploration, each revealing how curiosity, science, and daring missions shaped our journey into the cosmos. Chapter 1. Space exploration began the moment humans looked up and wondered what lived beyond the sky. The first real breakthrough came when early scientists built simple telescopes, revealing moons, craters, and swirling planets. These discoveries didn't just inspire curiosity, they created a roadmap for everything that would follow. The story of space exploration starts with a single question: what's out there? And answering that question changed our entire future. Chapter 2. In 1942, the German V-2 rocket became the first human-made object to reach the edge of space, proving that rockets could break free from Earth's grip. It was a military weapon, yet it unintentionally opened the door to cosmic exploration. After the war, captured technology and scientists helped reshape global research. This moment marked the beginning of a new era, one where nations realized space was no longer unreachable. Chapter 3. The space race ignited in 1957 when the Soviet Union launched Sputnik 1, the first artificial satellite. Its steady beeps from orbit stunned the world. Ordinary people looked up differently that night, knowing a human-made star was circling above them. Sputnik proved satellites were possible and pushed the United States into accelerating its own space ambitions. That single metal sphere rewired global priorities and sparked decades of innovation. Chapter 4. Just a month after Sputnik, the Soviets shocked the world again by sending Laika, a stray dog from Moscow streets, into orbit. Her mission showed that living creatures could survive weightlessness, but it also revealed the ethical cost of early space experiments. Laika never returned, yet her flight gave scientists vital biological data. Her sacrifice paved the way for safer human missions that would follow soon after. Chapter 5. On April 12, 1961, Yuri Gagarin became the first human in space, completing one orbit around Earth. His calm voice saying, "Let's go," became legendary. Gagarin's flight proved humans could survive spaceflight and re-entry, unlocking possibilities that once felt impossible. Nations paused to watch a new chapter of history open. His journey didn't just make headlines. It redefined what humanity could dare to attempt. Chapter 6. The United States answered quickly with Project Mercury, aiming to put an American in orbit. After several test flights, John Glenn orbited Earth 3 times in 1962, becoming a national hero. His mission validated NASA's engineering and boosted confidence in crewed space exploration. Mercury wasn't about long journeys, it was about proving the basics: launch, orbit, return. Those fundamentals became the bedrock for every future mission. Chapter 7. Project Gemini pushed human abilities further by testing spacewalks, docking, and longer missions. These tasks seem routine today, but in the 1960s, they were untested and risky. Astronaut Ed White performed America's first spacewalk, drifting freely above Earth with nothing but a thin tether. Gemini taught NASA how humans move, work, and endure in space. Without these lessons, the moon landing would have been impossible. Chapter 8. Apollo set its sights on a single bold goal: landing humans on the moon. The program demanded breakthroughs in navigation, computing, and spacecraft design. Engineers built the Saturn V, the most powerful rocket ever successfully flown. Every launch shook the ground and the imagination of millions. Apollo wasn't just a mission. It was a statement that humanity could reach worlds once thought untouchable through determination and science. Chapter 9. In 1969, Apollo 11 touched down on the moon, and Neil Armstrong took his famous first step. Millions watched as he described the moment as a giant leap for mankind. The mission collected lunar samples, deployed experiments, and proved humans could travel beyond Earth and return safely. That dusty footprint became a symbol of human possibility. For the first time, another world carried the mark of our presence. Chapter 10. Later Apollo missions expanded scientific work on the moon. Apollo 12 targeted a precise landing, showing accuracy was possible. Apollo 15 introduced the lunar rover, letting astronauts travel far from the lander. They brought back rocks, set up instruments, and uncovered clues about the moon's volcanic past. These missions weren't just adventures. They were science labs on alien soil, teaching us how planets form and evolve. Chapter 11. Apollo 17, the final moon mission, carried scientist-astronaut Harrison Schmitt, allowing trained geological eyes to study the lunar surface directly. The crew explored deep valleys and sampled ancient rocks that revealed billions of years of lunar history. Though Apollo ended, its scientific legacy remained enormous. The mission showed that combining human intuition with field science could unlock details no robot of that era could match. Chapter 12. After Apollo, NASA shifted focus to reusable spacecraft. This led to the Space Shuttle, designed to fly like a rocket and land like a plane. It carried satellites, labs, and astronauts into orbit for 3 decades. The shuttle changed spaceflight from rare events into regular missions, making construction and repair in orbit possible. Its design wasn't perfect, but it reshaped human access to space entirely. Chapter 13. One of the shuttle's greatest achievements was launching the Hubble Space Telescope in 1990. At first, Hubble's blurry images disappointed the world, until astronauts performed a repair mission that fixed its optics. After the correction, Hubble delivered breathtaking views of galaxies, nebulae, and distant stars. It transformed astronomy by showing the universe with clarity never seen before, and it proved humans could service complex machines in orbit. Chapter 14. Space stations became essential for long-duration research, beginning with the Soviet Salyut and later Mir. Mir hosted international crews and countless experiments, proving humans could live months in microgravity. It revealed challenges like muscle loss and radiation exposure, pushing scientists to develop countermeasures. Mir wasn't perfect. It had fires and collisions, but it taught the world how fragile and adaptable humans are in orbit. Chapter 15. The International Space Station emerged as the largest cooperative space project in history. Built piece by piece in orbit, it united agencies from the United States, Russia, Europe, Japan, and Canada. The ISS became a floating laboratory studying biology, physics, and human health in microgravity. Its long-term experiments shaped our understanding of how bodies change in space, guiding future plans for Mars missions and beyond. Chapter 16. Robotic probes expanded exploration far beyond human reach. NASA's Voyager missions, launched in 1977, flew past Jupiter, Saturn, Uranus, and Neptune, sending back detailed images of moons and storms. Voyager 1 eventually entered interstellar space, becoming the farthest human-made object. Each probe carried a golden record containing sounds and messages from Earth, a hopeful gesture toward any life that might one day discover them. Chapter 17. Mars exploration reached new heights with landers and rovers. Viking 1 and 2 captured the first clear images of Martian soil, while later rovers like Spirit and Opportunity searched for signs of ancient water. Opportunity exceeded its planned mission by more than a decade, traveling across dusty plains and craters. These machines transformed Mars from a distant red dot into a dynamic world with geological stories to tell. Chapter 18. Curiosity, a nuclear-powered rover, landed on Mars in 2012 with a dramatic sky crane maneuver. Its instruments discovered evidence of ancient lakes and chemicals necessary for life. Curiosity acted like a rolling laboratory, drilling rocks and analyzing their composition. Its mission deepened our understanding of Mars' habitability and pushed scientists to ask whether life might have once existed on the planet's quieter, wetter past. Chapter 19. Human dreams of visiting other planets rely heavily on better propulsion. Scientists continue developing ion engines, which use charged particles to deliver efficient thrust over long distances. Though slower to start than chemical rockets, ion propulsion pushes spacecraft to remarkable speeds over time. This technology powered missions like Deep Space One and Dawn, proving advanced engines could navigate asteroids and dwarf planets with precision. Chapter 20. Private companies began reshaping spaceflight in the 21st century. SpaceX introduced reusable rockets, dramatically lowering launch costs. The Falcon 9's ability to land upright became a defining moment in aerospace engineering. Meanwhile, companies like Blue Origin and Rocket Lab added competition and innovation. This shift marked a new chapter where commercial ambition joined scientific exploration, accelerating progress and expanding access to space for more nations. Chapter 21. The rise of reusable rockets changed mission planning entirely. Instead of treating boosters as disposable, engineers refined landing algorithms, grid fins, and throttle control. Each successful landing proved that spaceflight could be more like aviation, repeatable and cost-effective. This shift opened room for more scientific payloads, more experiments, and more frequent launches. Reusability didn't just save money. It reshaped the economics of reaching orbit. Chapter 22. Planetary missions continued with New Horizons, which flew past Pluto in 2015. Before this, Pluto was only a blurry pixel in telescopes. New Horizons revealed icy mountains, frozen plains, and a heart-shaped region that surprised everyone. Its data showed Pluto as a complex world, not a simple icy rock. The flyby proved how much detail a fast, lightweight probe could gather from the farthest reaches. Chapter 23. Saturn gained a dedicated explorer with the Cassini mission. Cassini orbited the planet for more than a decade, studying its rings, storms, and moons. The probe discovered liquid seas on Titan and geysers shooting from Enceladus, suggesting subsurface oceans that might host microbial life. When its fuel ran low, Cassini plunged into Saturn's atmosphere to avoid contaminating moons. Its finale ended a mission full of discoveries. Chapter 24. Jupiter's secrets were uncovered by the Juno spacecraft. which entered orbit in 2016. Juno's instruments peered through Jupiter's dense clouds to study its magnetic field, storms, and internal structure. It revealed that the planet's iconic Great Red Spot reaches deeper than expected, and that Jupiter's poles host swirling cyclone clusters. These data helped scientists understand how giant planets form and influence the architecture of solar systems. Chapter 25. Asteroid missions became more ambitious with Japan's Hayabusa and NASA's OSIRIS-REx. Hayabusa returned the first asteroid samples, while OSIRIS-REx touched down on Bennu and brought back pristine material older than Earth. These samples preserve ancient ingredients of the early solar system. By studying them, scientists gain clues about how planets formed and how organic molecules, the building blocks of life, traveled through space. Chapter 26. Comets, long considered mysterious wanderers, were explored up close by the Rosetta mission. Rosetta orbited Comet 67P and deployed a small lander named Philae. Although Philae bounced into a shadowed area, it still delivered valuable data. Rosetta mapped the comet's surface and tracked how it changed as it approached the Sun. The mission revealed that comets carry complex organic compounds, deepening questions about life's potential origins. Chapter 27. The discovery of exoplanets reshaped astronomy. Using the Kepler Space Telescope, scientists detected thousands of planets around distant stars by measuring tiny dips in brightness. Many were Earth-sized and located in habitable zones. These findings suggested that planets are common and that our galaxy may hold billions of potentially life-friendly worlds. Exoplanet research transformed the search for extraterrestrial life from speculation into systematic science. Chapter 28. The James Webb Space Telescope pushed observation deeper than ever before. With its infrared vision and large mirror, it captured light from some of the universe's earliest galaxies. Webb revealed atmospheric signatures on distant exoplanets and offered sharp views of star-forming regions. Chapter 29. Understanding space requires studying the Sun as well. NASA's Parker Solar Probe became the first spacecraft to fly through the Sun's outer atmosphere. It measured solar wind, magnetic fields, and energetic particles close to their origin. These data help predict space weather that can affect satellites and power grids on Earth. Parker's extreme mission demonstrated how technology can withstand environments once thought impossible to reach. Chapter 30. Lunar exploration returned with renewed purpose. NASA's Artemis program aims to land humans on the Moon again, including the first woman and first person of color. Artemis focuses on sustainable exploration, using new technology, lunar habitats, and partnerships with private companies. The plan includes studying water ice at the poles, which could support future missions. This new era treats the Moon not as a destination, but as a gateway. Chapter 31. China expanded its space ambitions with the Chang'e lunar program. Chang'e 3 delivered a rover. Chang'e 4 completed the first landing on the Moon's far side, and Chang'e 5 returned lunar samples to Earth. These missions demonstrated precise engineering and long-term planning. By collecting fresh material from the Moon's surface, China contributed new scientific data, proving that multiple nations can drive exploration forward in meaningful ways. Chapter 32. India made history with the Mars Orbiter mission, also known as Mangalyaan. Launched on a modest budget, it successfully entered Mars orbit in 2014, making India the first nation to reach the planet on its first attempt. The mission studied the Martian atmosphere and surface features. Its success inspired global respect and showed that cost-efficient engineering could achieve interplanetary results once reserved for major space powers. Chapter 33. Space tourism evolved from science fiction into reality. Early commercial flights carried paying passengers to the edge of space using suborbital rockets. Companies refined safety systems, training, and cabin designs to give civilians a brief taste of weightlessness. While still expensive, these flights marked a shift toward broader access to space. Tourism may seem small today, but it helps fund technology that could later support deeper missions. Chapter 34. Spacesuits advanced dramatically over the decades. Early suits were bulky and rigid, designed only to keep astronauts alive. Modern suits offer improved mobility, digital displays, and modular components. NASA, SpaceX, and international partners continue developing next-generation suits for the Moon and Mars. These designs must handle dust, radiation, and extreme temperatures. A suit is essentially a tiny spacecraft, and its evolution reflects human adaptability. Chapter 35. The search for life expanded with missions studying icy moons. Europa, Enceladus, and Titan appear to host subsurface oceans beneath their frozen crusts. Instruments detected hints of organic molecules and energy sources that could support microbes. Planned missions like Europa Clipper aim to examine these worlds in detail. These discoveries shifted the search for life from dry planets to hidden oceans that may be far more promising. Chapter 36. Deep space communication remains a critical challenge. The Deep Space Network, a global system of giant radio antennas, enables contact with spacecraft across the solar system. Signals traveling billions of kilometers arrive faint and delayed, requiring precise timing and powerful receivers. Without this infrastructure, missions like Voyager and New Horizons would be silent. Communication systems quietly shape every success in space exploration. Chapter 37. Space debris became a growing concern as more satellites entered orbit. Defunct spacecraft, fragments from collisions, and leftover rocket stages pose risks to operational missions. Scientists track thousands of objects to avoid dangerous encounters. Solutions include better disposal plans, cleaner launches, and future cleanup technologies. Handling debris responsibly ensures space remains usable for decades. Protecting astronauts and equipment from high-speed impacts. Chapter 38. CubeSats revolutionized access to space. These small, standardized satellites allow universities, startups, and smaller nations to run experiments at a fraction of traditional costs. CubeSats monitor weather, study radiation, test propulsion systems, and even visit asteroids. Their low price encourages rapid innovation, making space research more inclusive. Many groundbreaking ideas now begin as small cubes launched on larger rockets' spare capacity. Chapter 39. Mapping the cosmos requires powerful survey missions. Projects like Gaia measured the precise positions and motions of over 1 billion stars. This massive dataset reshaped models of the Milky Way's structure and history. By tracking stellar movements, scientists can trace past collisions between galaxies and predict future changes. Large-scale surveys show that understanding our home galaxy requires both technology and patient statistical analysis. Chapter 40. Human health research in microgravity reveals how fragile the body is. Astronauts experience bone loss, fluid shifts, and weakened muscles during long missions. Experiments on the ISS test exercises, diets, and medical tools to counter these effects. Understanding these changes is essential for future journeys to Mars, where crews may spend years away from Earth. Space medicine became as important as engineering in shaping safe exploration. Chapter 41. Rocket design matured through constant iteration. Engineers improved materials, guidance systems, and fuel efficiency to push payloads farther with less mass. Computers replaced analog controls, enabling precise burns and safer trajectories. These upgrades made missions more reliable and allowed spacecraft to carry heavier instruments. Every improvement, even small ones, stacked into major progress. Rocket science advanced not through single leaps, but through steady refinement over decades. Chapter 42. Space agriculture experiments began with simple seeds carried into orbit. Scientists studied how plants grow without gravity, discovering changes in root direction, water flow, and nutrient absorption. Modern experiments on the ISS now grow leafy vegetables and test closed-loop systems. Understanding how to grow food in space is essential for long missions, reducing dependence on Earth resupply. These early sprouts represent the future of off-world survival. Chapter 43. Meteorite research provides clues about the early solar system. Many meteorites contain minerals older than Earth, preserving chemical fingerprints from before planets formed. By studying their isotopes and organic molecules, scientists reconstruct events like supernova explosions and early collisions. Some meteorites even contain amino acids, suggesting that life's ingredients may have arrived from space. These rocks act as time capsules, helping decode our origins. Chapter 44. Landing on other worlds requires solving extreme engineering challenges. Thin atmospheres, rough terrain, and unknown hazards force missions to use parachutes, thrusters, radar, and sometimes skyplanes. Each landing teaches new lessons about balancing speed and precision. The success of landers on Mars, comets, and asteroids proves that complex maneuvers can work millions of kilometers away. These achievements expand the boundaries of what machines can do. Chapter 45. Satellites became vital to everyday life. They enabled GPS navigation, weather forecasting, communication networks, and disaster monitoring. Scientists track storms from orbit, predict climate patterns, and study ocean temperatures with remarkable accuracy. These systems blend engineering and data science, turning raw measurements into tools that help communities worldwide. Space exploration isn't only about distant planets. It's also about improving life on Earth through technology. Chapter 46. Radio astronomy transformed our understanding of the invisible universe. Telescopes detected signals from quasars, pulsars, and interstellar gas clouds. The discovery of pulsars, rapidly spinning neutron stars, proved that collapsed stellar cores can behave like cosmic lighthouses. Simon. Radio data also revealed the structure of the Milky Way's spiral arms. These findings came from listening rather than seeing, showing that space still hides secrets beyond visible light. Chapter 47. Gravitational wave detection opened a new way of observing the cosmos. Instruments like LIGO measured tiny ripples in space-time, created by colliding black holes and neutron stars. These events were impossible to detect with traditional telescopes. gravitational waves confirmed predictions from Einstein's theory of general relativity and unveiled violent cosmic events. This discovery launched a new era where astronomy uses both light and space-time vibrations. Chapter 48. Space robots became the hands and eyes of exploration. Robotic arms on the ISS repair equipment, capture satellites, and assist astronauts with risky tasks. Probes use robotic mechanisms to collect samples, drill surfaces, or deploy landers. These systems reduce mission risk and perform tasks too delicate or dangerous for humans. Robotics blend engineering and autonomy, extending human reach across vast distances. Chapter 49. Space weather forecasting gained importance as solar activity increased. Solar flares and coronal mass ejections can disrupt satellites, radio communications, and power grids. Monitoring the sun from orbit helps predict these events before they reach Earth. Agencies coordinate warnings to protect infrastructure and astronauts. Understanding space weather became essential for a world dependent on technology, turning solar physics into a practical field with global impact. Chapter 50. Exploration of the Moon revealed traces of water ice in permanently shadowed craters. Instruments aboard orbiters detected signatures of hydrogen, suggesting frozen deposits. Water on the Moon could support future missions by providing drinking water, oxygen, and even rocket fuel through electrolysis. This discovery transformed the Moon from a barren landscape into a strategic resource. It reshaped long-term plans for building sustainable human presence beyond Earth. Chapter 51. The study of planetary atmospheres revealed how worlds evolve. Venus showed a runaway greenhouse effect with crushing pressure and extreme heat. Mars displayed a thin, cold atmosphere that once supported flowing water. Comparing these planets helps scientists understand climate change and atmospheric loss. Each atmosphere acts as a historical record, preserving clues about past environments. Through these comparisons, Earth's uniqueness and its fragility became clearer. Chapter 52. Gravity assists became a powerful tool for deep space travel. By slingshotting around planets, spacecraft gain speed without extra fuel. Missions like Chapter 53. Space telescopes across different wavelengths revealed a layered universe. Infrared observatories studied cool stars and dusty regions. X-ray telescopes detected black hole activity, and ultraviolet missions traced hot gas in galaxies. Each wavelength offered a new perspective, much like switching tools in a lab. By combining these observations, astronomers built a more complete picture of cosmic processes, from star birth to galaxy evolution. Chapter 54. Sample return missions advanced scientific accuracy. Bringing material back to Earth allows researchers to use advanced instruments too large for spacecraft. Apollo lunar rocks, stardust comet samples, and asteroid material from Bennu and Ryugu all provided precise data about organic chemistry and formation processes. These samples act as reference points for remote sensing, improving calibration and interpretation of future missions. Chapter 55. Interplanetary navigation relies on star trackers, gyroscopes, and radio signals. Spacecraft constantly adjust orientation using tiny thrusters to stay on course. Even a small drift can accumulate into major errors over millions of kilometers. Navigation teams on Earth analyze signal delays and Doppler shifts to refine positions. This careful choreography allows probes to reach targets with astonishing accuracy despite the vast distances. Chapter 56. Space-based Earth observation revolutionized environmental science. Satellites track deforestation, glacier retreat, ocean currents, and atmospheric pollution with global coverage. Time-lapse data reveals long-term trends that ground observations might miss. These insights guide conservation efforts, climate models, and disaster response. Space technology became a crucial tool for understanding Earth's health. Connecting exploration with environmental responsibility. Chapter 57. The study of cosmic rays uncovered high-energy particles arriving from distant galaxies. These particles travel near light speed and provide clues about supernova explosions and black hole jets. Instruments on spacecraft and space stations measure their composition and intensity. Understanding cosmic rays is essential for astronaut safety, as they pose radiation risks during long missions. Their study links astrophysics with human survival in deep space. Chapter 58. Reusable spacecraft concepts extended beyond rockets. SpaceX's Dragon capsules return cargo and crew safely, while other designs explore rapid refurbishment for frequent flights. Engineers aim to reduce turnaround times, making space travel more routine. This approach mirrors aviation practices, shifting exploration from rare events to regular operations. Reusable vehicles may eventually support orbital stations, lunar bases, and interplanetary missions. Chapter 59. Solar sail technology tests propulsion without fuel. These sails capture momentum from sunlight, slowly accelerating spacecraft over time. Missions like Icaros and LightSail demonstrated controlled flight using reflective materials and precise orientation. Solar sails could enable lightweight probes to reach distant targets or even travel between stars. The concept turns sunlight into a continuous engine, offering a sustainable method for long-distance exploration. Chapter 60. Lunar orbiters mapped the Moon in detail, revealing mountains, valleys, and impact basins with high resolution. Instruments detected minerals, temperature patterns, and radiation levels across the surface. These maps help select landing sites and study the Moon's geological history. High-resolution mapping transforms the Moon from a simple gray sphere into a complex world shaped by volcanic activity and ancient collisions. Chapter 61. Mars' polar ice caps store vast amounts of frozen water. Seasonal changes cause them to grow and shrink, creating dramatic patterns. Studying these caps helps scientists understand the planet's climate cycles and history of water. Ice may serve as a resource for future explorers, providing drinking water or fuel. Polar research transforms Mars from a dry desert into a dynamic world with potential for human use. Chapter 62. Venus missions revealed extreme conditions. Temperatures reach 460 degrees Celsius, and surface pressure is 90 times Earth's. Thick clouds of sulfuric acid block visible light, requiring radar mapping for surface studies. These harsh conditions ended early landers quickly, but data showed volcanic plains and vast mountain ranges. Venus teaches the consequences of greenhouse effects and highlights engineering challenges for exploring hostile worlds. Chapter 63. Titan. Saturn's largest moon hosts rivers and lakes of liquid methane and ethane. Its thick atmosphere and organic-rich chemistry mimic early Earth conditions. Huygens probe revealed dunes, hills, and potential cryovolcanoes. Titan's exploration inspires ideas about prebiotic chemistry and life's building blocks. Studying these distant environments informs theories of planetary evolution and the diversity of chemical pathways in the solar system. Chapter 64. Asteroid mining became a topic of scientific and commercial interest. Rich in metals like platinum, nickel, and rare earth elements, asteroids could provide resources for space industry. Missions like Hayabusa 2 and OSIRIS-REx study surface composition and sampling techniques. Learning to extract materials off-world could reduce costs of deep space construction and make long-duration missions more feasible. Science and industry converge in these small bodies. Chapter 65. Space interferometry allows telescopes to work together as one large instrument. By combining data from multiple observatories, scientists achieve higher resolution than a single telescope could. Techniques like radio interferometry reveal distant galaxies, star clusters, and black holes with clarity. Interferometry transforms observational power, enabling discoveries that expand our understanding of the universe's structure and evolution. Chapter 66. Exoplanet atmospheres reveal clues about potential habitability. Spectroscopy detects water vapor, methane, and carbon dioxide, helping classify planets as rocky, gaseous, or ocean worlds. Understanding these atmospheres guides the search for life beyond Earth. Each new detection adds context, showing that Chapter 67. The study of micrometeorites informs both planetary science and spacecraft design. Tiny particles constantly bombard Earth and other planets, shaping surfaces over billions of years. Spacecraft shielding must account for these high-speed impacts. By collecting micrometeorites in the atmosphere or analyzing surface craters, scientists learn about the solar system's formation and hazards that travelers may encounter in space. Chapter 68. Orbital refueling concepts could extend mission lifetimes dramatically. Fuel depots in orbit allow spacecraft to resupply before heading deeper into the solar system. Experiments test docking, transfer systems, and automated handling of cryogenic propellants. These technologies reduce dependency on single launches and enable multi-target missions. Orbital refueling represents a step towards sustainable, long-duration exploration beyond low Earth orbit. Chapter 69. Space medicine studies long-term effects of radiation and microgravity. Astronauts on the ISS help researchers develop countermeasures such as exercise routines, diet plans, and shielding technologies. Findings also support medicine on Earth, improving bone, muscle, and cardiovascular health. Space becomes a laboratory where human biology is stress-tested, preparing for journeys that may last years and ensuring crews return safely. Chapter 70. The study of cosmic dust offers clues about planet formation. Dust particles from comets, asteroids, and interstellar space contain silicates, organics, and minerals. Instruments aboard orbiters and probes capture and analyze these grains. Dust plays a role in forming planetary cores and atmospheres. By tracing its composition and origin, scientists reconstruct processes that shaped the early solar system, linking tiny particles to massive planetary systems. Chapter 71. Mars' atmosphere is mostly carbon dioxide, but thin enough that water can't remain liquid on the surface. Dust storms can engulf the planet for weeks, altering temperature and visibility. Understanding these conditions is vital for future human missions. Climate models based on orbital and rover data guide landing site selection and habitat design. Studying Mars's environment prepares humanity for safe exploration and potential colonization. Chapter 72. The study of magnetospheres revealed how planets protect themselves from solar radiation. Earth's magnetic field deflects charged particles, forming the Van Allen belts. Jupiter's massive magnetosphere traps intense radiation, shaping its moon's surfaces. Understanding these magnetic shields is essential for spacecraft design and human safety. Magnetospheres also provide insight into planetary formation, internal structure, and the potential for life on other worlds. Chapter 73. Europa, one of Jupiter's moons, has a subsurface ocean beneath a thick ice shell. Tidal forces from Jupiter generate heat, keeping liquid water from freezing completely. Future missions aim to probe the ocean for signs of microbial life. Studying Europa helps scientists understand how water and energy interact on icy worlds. The moon represents one of the best chances to discover life beyond Earth. Chapter 74. Enceladus, Saturn's moon, shoots water-rich plumes from its south pole. These geysers carry organic compounds into space, making them accessible to orbiting probes. Cassini analyzed the plumes, detecting hydrogen and other chemicals that could support microbial life. Enceladus demonstrates that habitable environments may exist far from the Sun. Its plumes provide a natural sampling opportunity, reducing the need for complex landing missions. Chapter 75. Mars rovers use advanced instruments to detect minerals that form in water, including clays and sulfates. These minerals record the planet's wet past and guide the search for ancient habitable environments. By drilling into rocks and analyzing chemical signatures, rovers reconstruct local histories. Each sample adds context for understanding Mars' evolution and whether life ever existed on the planet's surface. Chapter 76. Astrobiology studies how life might arise elsewhere. Experiments test extremophiles, organisms that survive extreme heat, cold, acidity, or radiation. Understanding these organisms informs the search for life on other planets and moons. Combined with planetary data, astrobiology helps identify the most promising targets, bridging biology, chemistry, and space science. It expands the definition of habitable worlds beyond Earth-like conditions. Chapter 75. Mars rovers use advanced instruments to detect minerals that form in water, including clays and sulfates. These minerals record the planet's wet past and guide the search for ancient, habitable environments. By drilling into rocks and analyzing chemical signatures, rovers reconstruct local histories. Each sample adds context for understanding Mars' evolution and whether life ever existed on the planet's surface. Chapter 76. Astrobiology studies how life might arise elsewhere. Experiments test extremophiles, organisms that survive extreme heat, cold, acidity, or radiation. Understanding these organisms informs the search for life on other planets and moons. Combined with planetary data, astrobiology helps identify the most promising targets, bridging biology, chemistry, and space science. It expands the definition of habitable worlds beyond Earth-like conditions. Chapter 79. Gravity assists, also called slingshots, have enabled missions to reach multiple planets with minimal fuel. Voyager and Cassini relied on carefully timed planetary flybys to gain speed and adjust trajectory. Planning these maneuvers requires precise calculations and knowledge of planetary motion. Gravity assists transform celestial bodies into natural propulsion tools, allowing spacecraft to explore more destinations efficiently. Chapter 80. The study of craters informs planetary history. Impacts from asteroids and comets shape surfaces, create basins, and redistribute material. By analyzing crater size, distribution, and age, scientists estimate surface ages and record solar system events. Crater studies also help predict hazards for spacecraft and guide safe landing site selection. They act as historical markers, tracing billions of years of cosmic collisions. Chapter 81. Mars dust devils and global storms illustrate the power of wind on a dry planet. Dust lifts alter temperature, reduce solar panel efficiency, and shape surface features. Rovers monitor these storms to adapt power usage and navigation. Studying Martian weather helps scientists predict conditions for future human missions. Understanding atmospheric dynamics on Mars is crucial for survival and long-term exploration planning. Chapter 82. The Moon's surface is covered by regolith, a layer of fragmented rock and dust formed by billions of years of impacts. Regolith protects deeper layers but poses challenges for landing and construction. Lunar rovers and landers analyze its composition, revealing history of impacts, solar radiation, and volcanic activity. Studying regolith informs engineering for habitats and resource extraction, turning moon dust into valuable knowledge. Chapter 83. Planetary geology uses remote sensing to study volcanoes, canyons, and craters from orbit. Mars shows evidence of ancient river valleys and massive volcanoes like Olympus Mons. Venus's surface, mapped by radar, reveals vast lava plains and tesserae. Understanding geological processes helps reconstruct planetary histories and potential for past habitability. Geology links observation to dynamic processes shaping planetary surfaces over billions of years. Chapter 84. Satellites detect changes in Earth's ice sheets and glaciers, tracking climate shifts over decades. Space-based monitoring reveals melting trends, sea level rise, and glacial retreat. These data support climate models and inform adaptation strategies. Observing Earth from orbit provides a unique perspective, connecting exploration technology with environmental science. Space tools are essential for understanding and protecting our home planet. Chapter 85. Exoplanet research identifies Earth-like worlds in habitable zones, using transit photometry and radial velocity measurements. Thousands of candidates have been discovered, some with atmospheres that could support water. These findings challenge assumptions about planetary rarity and inform priorities for future telescopes. The study of distant worlds shifts space exploration from our solar system to the galaxy, emphasizing diversity and possibility. Chapter 86. Comet 67P, visited by Rosetta, revealed surface variations, pits, and layers of dust and ice. The lander Philae sampled material and provided chemical analyses. Studying comets uncovers primordial material from the solar system's formation. These icy bodies act as natural laboratories, preserving organic molecules and volatile compounds. Comet missions offer insight into the ingredients that shaped planets and possibly life itself. Chapter 87. Lunar lava tubes are underground tunnels formed by flowing lava. They may offer natural shelter for future habitats, shielding humans from radiation and temperature extremes. Mapping and exploring these structures could allow construction of bases that minimize surface risks. Studying lava tubes combines geology, engineering, and exploration planning, offering realistic solutions for long-term human presence on the Moon. Chapter 88. Jupiter's moon Io is the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions, lava flows, and sulfur deposits. Tidal heating from Jupiter's gravity powers this activity. Studying Io provides insight into planetary interiors and the effects of gravitational forces. Active worlds like Io demonstrate that dynamic geology is not limited to Earth, expanding understanding of planetary diversity. Chapter 87. Lunar lava tubes are underground tunnels formed by flowing lava. They may offer natural shelter for future habitats, shielding humans from radiation and temperature extremes. Mapping and exploring these structures could allow construction of bases that minimize surface risks. Studying lava tubes combines geology, engineering, and exploration planning, offering realistic solutions for long-term human presence on the Moon. Chapter 88. Jupiter's moon Io is the most volcanically active body in the solar system. Its surface is constantly reshaped by eruptions, lava flows, and sulfur deposits. Tidal heating from Jupiter's gravity powers this activity. Studying Io provides insight into planetary interiors and the effects of gravitational forces. Active worlds like Io demonstrate that dynamic geology is not limited to Earth, expanding understanding of planetary diversity. Chapter 91. The Moon's south pole is rich in permanently shadowed craters that may hold water ice. These regions never see sunlight, preserving frozen deposits for billions of years. Water could be used for drinking, oxygen, and fuel, supporting long-term missions. Mapping and accessing these craters requires precision engineering. The South Pole represents a strategic target, turning the Moon into a practical stepping stone for deeper space exploration. Chapter 92. Mars dust storms can become global, reducing sunlight and affecting solar-powered rovers. Tracking storm patterns allows mission teams to protect equipment and plan operations. Dust also contributes to erosion and surface changes, revealing dynamic planetary processes. Understanding these phenomena helps engineers design resilient habitats and instruments, preparing for future human explorers who will live and work on the Martian surface. Chapter 93. Asteroid Bennu, visited by OSIRIS-REx, showed a surface covered with loose rocks, challenging assumptions about small bodies. Samples collected contain primordial material from the early solar system. Studying Bennu's composition informs models of planet formation and the distribution of organic compounds. These missions demonstrate that small, distant bodies can hold keys to understanding the origin of life and the evolution of our solar system. Chapter 94. Space telescopes allow scientists to detect galaxies billions of light years away. By observing their light and redshift, astronomers study the early universe's formation and expansion. Instruments capture ultraviolet, visible, and infrared data to reveal star formation, supernova, and black hole activity. These observations reconstruct cosmic history, providing context for the evolution of galaxies and the large-scale structure of the universe. Chapter 95. Mars sedimentary rocks preserve ancient environments. Rovers analyze layered formations to detect past water activity, volcanic eruptions, and wind-driven deposition. These geological records help reconstruct the planet's climate history and assess potential habitats for life. Studying sedimentation bridges chemistry, geology, and planetary science, turning rocks into storytellers that reveal Mars' dynamic past. Chapter 96: Exoplanet Imaging revealed atmospheres with clouds, haze, and chemical composition. Instruments detect water vapor, carbon dioxide, and methane, helping classify planets and assess habitability. Direct imaging allows scientists to study planetary weather and dynamics remotely. Observing exoplanet atmospheres expands knowledge of planetary diversity and informs the search for worlds that could harbor life beyond our solar system. Chapter 97: Satellites monitor Earth's magnetic field, detecting changes that indicate solar activity or core dynamics. Shifts in the field affect navigation systems, communication, and radiation exposure. Tracking geomagnetic variations helps scientists understand the planet's interior and protect technological systems. Space-based monitoring ensures both scientific understanding and practical applications for modern life dependent on orbiting infrastructure. Chapter 98: The study of cosmic microwave background radiation revealed conditions just after the Big Bang. Observatories like COBE, WEM, and Planck measured temperature fluctuations across the sky. These patterns encode information about the universe's age, composition, and structure. Cosmic background studies connect cosmology with fundamental physics, allowing humans to peer into the earliest moments of existence and understand the universe's evolution. Chapter 99: Mars orbiters map mineral composition, ice deposits, and surface features. Data from instruments like spectrometers reveal chemical diversity and potential water sources. These maps guide rover missions, landing site selection, and future human exploration planning. Orbital surveys provide global context for localized observations, linking detailed surface data with planetary-scale patterns, improving our understanding of Mars as a complex, evolving world. Chapter 100: The pursuit of space exploration combines curiosity, technology, and perseverance. From telescopes and rovers to orbiters and landers, each mission uncovers new facts and challenges assumptions. Science and engineering work together to explore planets, moons, comets, and distant stars. Every discovery builds on the last, creating a continuous story of human ingenuity. The history of space exploration proves that the universe rewards those willing to reach beyond. Space exploration continues to push boundaries, revealing new worlds and mysteries. Remember, every discovery starts with a question, and the universe is waiting